Swayam Prabha. Digital India. Educated India.
Welcome to lecture 3 of module 6. In this module, we have been discussing on condensation and boiling heat transfer. In last couple of lectures, we have discussed on condensation heat transfer phenomena. Now, today and the next lecture, this couple of lectures, we will be discussing on boiling heat transfer phenomena. And as we know that both boiling and condensation, they are related to phase change operations, and they have a significant industrial importance, practical importance, particularly from the chemical engineering point of view. Okay. So, today's lecture we are going to discuss on fundamentals of boiling phenomena. Okay. So, as we have discussed that boiling and condensation both are phase transfer phenomena, and in case of boiling the phase transfer leads to conversion from a liquid phase to the vapor phase, that we all know. Now, what happens that boiling is very practically important or significant from chemical engineering point of view. Like we know that distillation column is one very common separation equipment from chemical engineers point of view, and in the distillation column we need to have a reboiler unit where the liquid is vaporized. Okay. So, the applications of boiling heat transfer, we can see that if we try to see, there are several applications. As I told, first one is we can say the reboiler in the distillation column. Then many a times we need to have high pressure steam, high pressure steam generation. As we understand that that at atmospheric pressure water boils at 100 degree centigrade, which is the boiling point of pure water. Now, what happens is many a times we need to increase the pressure and then and boil water to get high pressure steam. So, the temperature of that steam will be saturated steam at that high pressure will be much higher than 100 degree centigrade, and this high pressure steam, which is saturated steam, which is at a very high temperature, is many a times used for heating up certain fluid. Now, these fluids, heating up of the certain fluid is very much necessary for many industrial operations, like many reactors. When we need to have some reactions to take place, then that feed may be requiring to have some elevated temperature. Similarly, like even in the distillation column itself, the feed may be, that available feed may be at a lower temperature, we may have to increase the temperature of the feed, and then we have to put into the distillation unit. So, like that. So, application of high pressure steam is very wide in case of chemical engineering point of view, and this high pressure steam generation is nothing but by use of boiling phenomena and boiling heat transfer. So, we need to have a reboiler unit designed for high pressure steam generation. Okay. Then many a times we require that the reactant should be in the vapor form in case of a reactor. So, reactants in a reactor. So, many times we see, as I told, that the reactants needs to be in vapor form and then it is placed into the reactor. Now, how to get that vapor of the reactant initially may be in the liquid form and then it is to be vaporized. So, the boiling does not mean that it will be only for water, the boiling can happen to any other solvent of interest, and the temperature may be depending upon the relative volatility, depending upon the volatility of the particular solvent. So, if the solvent is highly volatile, then or that more volatile than water, then that boiling temperature will be lower than water boiling temperature and at that same pressure conditions. And if the volatility of the solvent is less compared to water, then it requires higher temperature for it to be boiled at the same pressure condition. So, we should understand that boiling is a very important phenomena from engineering aspect, from industrial importance, and boiling heat transfer is because of that reason of equally important to us, and we should learn how the boiling phenomena take place and what kind of relationships are used to evaluate the value of heat transfer due to boiling. Okay. Now, we know that how the boiling takes place. We will now in this lecture we will try to concentrate on some basic mechanisms and the concepts of boiling phenomena. Now, what happens is that when a surface is immersed in a liquid, then what happens, and the surface is heated, and so surface temperature will be higher than the temperature of the liquid, and then the liquid will take up some point of time, the liquid will go on heated, will be heated, and then after some point of time it will start boiling. Now, this boiling phenomena can be divided into two parts. One is called pool boiling, another is forced convection boiling. Okay. Now, in case of pool boiling, we can understand there is a liquid pool. Pool of liquid is there, which is you can consider as a stagnant liquid is there, and this in the liquid, inside the liquid there is a surface which is heated up, and because of that heating phenomena that liquid starts boiling. So, this is simply called as the pool boiling, and another one is called forced convection boiling. Under that situation, what happens that there is a motion that is being given by some external pump or external energy is being placed, so that the material or the fluid or the liquid while it is boiling, it moves along. So, it is called forced convection boiling. So, it is here it is that the liquid does not remain as a stagnant liquid, it is in the under moving condition, or the boiling medium is basically is in under moving condition. That is why it is called forced convection boiling. Now, in the pool boiling, we can say that this is also can be called up that one case is subcooled or local boiling, and another case is called saturated or bulk boiling. When we say about the subcooled or local boiling, that means if the temperature of the liquid is below the saturation temperature, if the temperature of the liquid is below the saturation temperature, then it is called subcooled or local boiling. That means what is happening, that boiling starts, and then after that again that vapor bubbles forms, and then again it is collapsed. So, this is called subcooled or local boiling, and then saturated or bulk boiling. That means, in this case the saturation temperature of the liquid is equal to the or more than the boiling temperature of the liquid. So, it is the saturation temperature of the liquid. So, that is why it is called the saturated boiling or bulk boiling. We will see that. So, what happens is when a surface is heated, in case of, so our main discussions would be at present would be based on this pool boiling phenomena. In the pool boiling phenomena, what happens is that, as we discussed, there is a stagnant fluid, fluid means liquid here, and there is a surface, and if the surface is heated, then what happens that initially that means the surface is of higher temperature than the liquid over there. So, this is called the excess temperature. So, surface has got some excess temperature. If we can say that this excess temperature as T W minus T saturation is called T E is the excess temperature, T W is the wall temperature, and T saturation is the saturation temperature of the saturated liquid, temperature of the saturated liquid. Saturated liquid means the liquid at its boiling point, or that is called saturated liquid. Similarly, the vapor in equilibrium with the saturated liquid is called the saturated vapor, and that expected temperature of the saturated vapor will be in equilibrium with the temperature of the saturated liquid. That means, they are more or less the same. Okay. Now, what happens is that when we have to have some kind of boiling phenomena to start, so we need to have some excess energy, excess temperature for this wall, wall of the surface. So, if we maintain little excess, then what happens that the liquid layer immediate vicinity, they get heated up, and then there is no formation of the bubbles being formed. The only thing what happens is that there will be some in most of the times that in that situation, if the T is very small, then a vapor will come up, and heat transfer will be in the form of vapor evaporation, and there will be not formation of any bubbles. Now, once we go on increasing the temperature little bit, then what will happen that there will be bubble formation on the surface, minute bubble formation, fine bubble formations will be there on the surface, and then these bubbles will try to go up, but it cannot go much upward, because that subsequent layers in the upward directions, there will be condensation, the temperature will be low of the liquid, temperature will be low, and therefore, the bubbles, there will be condensation, and then the bubble will collapse. And then what happens if you maintain the further temperature, further difference in temperature, then what will happen that more bubbles will start forming, and they will try to cover up the whole liquid, and then they will rise till the surface, free surface of the liquid. Free surface of the liquid means the surface of the liquid which is in contact with the atmosphere. So, free surface of the liquid, they will come, and there they will burst. So, this way the bubbles will come, and then if we do further heating, there could be a formation of films due to the breakages and coalescence of the bubbles. So, these things we are going to discuss with the help of a curve that is called boiling curve. So, boiling curve is a curve that is very important thing for us, that boiling curve, and this boiling curve is being studied in case of pool boiling phenomena. It is that a curve that represents that variations of heat flux versus excess temperature. So, how the heat flux, or sometimes it is written as heat transfer coefficient, the variation of heat transfer coefficient with excess temperature. As we discussed, excess temperature is the differential temperature between the surface and the saturation temperature of the liquid, temperature of the saturated liquid. So, the difference is the excess temperature, and that boiling curve is a plot of heat transfer coefficient and a logarithmic values of the heat transfer coefficient versus the excess temperature. And we will see that in the boiling curve, there are various regimes are there, and these regimes have got lot of physical significance. Here in this figure 1, we can see this the boiling curve, and in this boiling curve there are a lot of regimes are there. We can see that they are classified into regime 1, 2, 3, 4, 5 and 6. There are 6 regimes, and we will see there that it is a log of heat transfer coefficient versus that excess temperature that is being plotted, and we see that, and when the excess temperature is less, then there is a different type of behavior, and gradually if we go ahead, then the behavior is little different. Now, if you see from the figure here, in the figure 2 here, that we can understand the case 1 is a phenomena that is called. So, if we see that regime 1, it's a region in the boiling curve. It is called it is also called as that free convection or interfacial evaporation region, interfacial facial evaporation region. Now, what happens in this region? Salient features of this region is that TE, the excess temperature is nearly maximum of 2 degree centigrade. The excess temperature is, though in the figure it is plotted in terms of degree Fahrenheit, they are very close to each other, because of considering the range of these temperature, excess temperature. So, this is in a very much lower range, it is in log scale. So, excess temperature is within this 2 degree centigrade in case of interfacial evaporation region. And then what happens in this region is, and this region is valid, we can see from the figure that it is from A to B. In this region, this is valid, and you can see that there is a straight line. Straight line means heat transfer coefficient is increasing like a linear manner, and this is a region, as we said, that it is the mostly the free convection heat transfer takes place. So, free convection phenomena is prevalent over here, and heat transfer coefficients value can be calculated using correlations related to free convection heat transfer. So, what is happening in this case, as we have discussed and we have shown in this figure. So, in the figure 1, the first figure, if you see in the figure 2 in the first one, if we see that there will be some the vapor formation will be there, and these vapors will go up because of density differences, the vapors will go up. There is no formation of the bubbles at this particular moment, and what happens that liquid elements coming in contact with the surface, they are getting heated up and they are becoming lighter, and they will try to go upward, and this is the situation that happens. And in this case, the motion of the fluid is due to free convection, and therefore, it is the free convection heat transfer that is prevalent over here. Another point, we should say that the hot liquid vaporizes only at the free top surface. That means what we can so therefore, it is called interfacial evaporation region, because at the top surface and atmosphere there is an interface. In that interface the evaporation takes place. This is viewed like this way. Now, then comes the region 2, and in region 1 we can say that it is from A to point A to B, okay, that we can see from the curve is from A to B. Now, from B to D, actually I will say that if we say region 2 and 3, they cover up from B through C to D. So, this is what is happening. Now, actually there are two parts. Region 2 indicates BC and 3 indicates C to D. Okay. These are the two regions. Now, what is happening if we see this, that region 2 and 3, that is from B through C to D, this whole part is called as nucleate boiling region. This is called nucleation or nucleate boiling region. Okay. Now, what happens is, for region 2, that means from B to C, in this case what happens, that bubble starts forming on the surface, and that is called a nucleation. So, nucleation starts, but the bubbles cannot reach to the surfaces, and here the temperature difference. So, T is nearly 2 to 6 degree centigrade, and here bubbles begin to form, but can't reach the surface, free surface. So, we can say that at point B is the onset of nucleation, point B is onset of nucleation, then if we just go on, then if we try to see for region 3, here it is from C to D. So, if we go back again to the picture, what we will see here, that for B to C is the second picture, very few bubbles are formed, because the temperature is not that much sufficient for so many bubbles to form, and then these bubbles also cannot go till the surface, because what is happening, the bubbles will start growing till certain extent, and then after that layer of the liquid is not or rather is at lower temperature. So, then what will happen, the bubbles collapse. Okay. But the case 3 is the situation when the bubbles will go upward. So, here the bubbles are going upward, and then bubble reaches to the surface, free surface, and so we can say that from C to 3, here the T is nearly 7 degree centigrade to 35 degree centigrade. This is a rough estimate of that, and here bubbles are generated and bubbles are formed rapidly. And vigorously, okay, and they reach the free surface. Then what happens, that near point D, that means when the temperature is, when T excess is nearly equal to 35 degree centigrade or so, then what happens, the bubble starts a lot of activities, doing lot of activities, there will be lot of breakage and coalescence of the bubbles. So, breakage of bubbles take place. Anyway, before we go to that part, what we can see is that in this we can see that because of the formation of the bubbles, we can see that there is almost a sharp increase in the heat transfer coefficient. So, we can see that there is a sharp increase in the heat transfer coefficient. Initially, the heat transfer coefficient increases not that sharp, and later on in the second phase, that means in the region 3, when there is a vigorous boiling is taking place, that means lots of bubbles are being formed, and so bubbles are carrying the energy to the top, and therefore, they are increasing the heat transfer coefficient, and rate of heat transfer is also increased like anything. So, this is of most important, this region, this nucleate boiling region is of most important use for industrial applications, and because here the heat transfer rate is very high, heat transfer coefficient is also very high, and nucleation boiling region is therefore is very much important. Now, if we further go on increasing the temperature, we are reaching to region 4. That means in the region 4, if I say, what happens that because of the bubbles formation is very vigorous, there will be lot of breakage and coalescence of the bubbles, and that lead to formation of films, formation of more increase or rather further increase in TE excess temperature. So, what will happen, that formation of film over the surface, hot surface. Now, the question is that this formation of the film is a momentary formation of film of vapor. Okay. That means, what is that? Sometimes the film appear and then again disappear, leaving a free surface for bubble formation. So, what does it mean? It means that we have a surface, and on the surface there are a lot of bubble formations, and because the more number of bubbles, so bubbles may coalesce and give a film, and then this film gets heated up, they go upward, leaving the free surface, again new film, again a lot of new bubbles, then film, like that it happens. And therefore, what happens in the boiling curve is that heat transfer rate is gradually decreased. It is not that suddenly it is decreased, because what is happening? That film of the vapor is acting as a blanket, but this blanket is not a permanent blanket, it is a temporary blanket, and that offers some amount of heat transfer resistance, but this heat transfer resistance is not is persisting for a continuously longer time. So, what happens is, therefore, this region is called film boiling region, but it is called partial nucleate or transition boiling. Or transition boiling. Actually, it is a part of film boiling region. Okay. So, this is of very important phenomena. So, film boiling region is the region that is coming after all, which is called the stable film boiling. So, region 5, it's so region 4 is between D to E, and region 5 is between E and F, and here in this region, so little increase in TE makes a stable film acting as blanket, stable and permanent blanket of vapor on the hot surface. Okay. And we know the thermal conductivity of the vapor is poor, and therefore, it acts as a strong resistance for heat transfer, and therefore, we can see there is a drastic reduction in the heat transfer coefficient value, and this is the region which is called stable film boiling region, and in this region heat transfer coefficient is drastically reduced. So, we can say in this region heat transfer coefficient is drastically reduced. Now, if we go to region 6, in this region what happens? Again we see there is a sharp rise of heat transfer coefficient or alternately the heat transfer or heat flux rate. I am sorry, heat flux itself is there. So, heat flux or alternately the heat flux, sharp rise in the heat flux, and this is happening. Now, why this is happening? If we see the temperature range in this case, if we again go back to the boiling curve, if you see the temperature range, it is somewhere more than 100,000 degree Fahrenheit or so. So, it's a huge temperature. So, delta T is very high, and at that condition what we expect is T is very high. So, what we expect is a radiation to come into picture. So, we expect radiation becomes a significant mechanism of heat transfer. Okay. So, these things we will be discussing little later regarding the radiation heat transfer. We will be discussing sometimes later. We will discuss in details on radiation. However, in this case, so radiation plus boiling, so it is a combined phenomena that makes. So, basically it is a combined phenomena that makes the heat transfer faster. Then question comes, should we operate at this temperature? No, we will try to avoid operate at this temperature, because there is a problem that many a times come, which is called boiling crisis. So, boiling crisis is a situation when, due to excessive temperature difference between the surface and the liquid, it may happen the surface may get melted, surface may melt down, may get melted or burnt out, and due to large excess temperature T, and then this phenomena is called boiling crisis. So, we should try to avoid reaching such kind of crisis situations. So, what has to be done? Our target, and then another thing we should see that there is many a times uncontrolled heating may lead somebody to reach from point D to point G. So, uncontrolled heating, so little bit of or rapid heating, so rapid change in excess temperature may lead to formation of a situation of boiling crisis or a situation of or reaching a level of radium 6. That is a highly possibility. So, therefore, we have to be very careful while designing a reboiler or boiling situation or boiler design. We have to be careful that it never goes for this regime 6 or it never goes for any boiling crisis situation. And as I told you, there is a quick jump from point D to point G may take place, and this happens due to uncontrolled heating that may lead to uncontrolled increase in the excess temperature. Therefore, we should always try to constrain ourselves to, in case of boiling situation, constrain ourselves little lower than the values of temperature, excess temperature compared at D. So, we have got some excess temperature at point D. So, we should constrain ourselves at value of E, which is little lower than the value of T E at point D. Okay. So, that is called the operating temperature of the operating excess temperature, that we can say. Now, while discussing these things regarding this boiling, so we have found out that best possible operating region for boiling is the nucleate boiling region with TE less than the TE for point D to reach. So, this is to avoid boiling crisis phenomena and safety from having uncontrolled heating that may lead to switching from point D to point G. Okay. Now, in this context, we will discuss a phenomena that is called Leidenfrost phenomena. So, Leidenfrost phenomena, it's a phenomena that is being observed by Leidenfrost in 1756. Observed in 1756. What is this phenomena? The phenomena is something like that, like say if a vapor droplet, sorry, if a water droplet falls on a hot surface, then what happens? Some kind of dancing phenomena that takes place. That means the if a water droplet falls on a hot surface, then it bounces up and down for some time and then vanishes. So, this is called a dancing phenomena for the bubbles, for the droplet. Again I am repeating. So, if we have a water droplet that is falling from falling on a hot surface, then there is a possibility that this droplet will bounce up and down for some times and then it will vanish. And this particular phenomena, which is kind of dancing of the droplet that takes place, is called the Leidenfrost phenomena. Now, what is happening actually in this case? As I told you that droplet is falling on a hot surface. So, that means a considerable temperature difference is there between the droplet and the hot surface. Okay. So, considerable temperature difference is there. It is something like, again we can correlate this for the case of say drop of liquid nitrogen or liquid air on floor. So, if incidentally if a drop of liquid nitrogen or liquid air is fallen on the floor, then what is happening? Then also the temperature difference will be sufficiently high, because we know that liquid nitrogen temperature is in minus some 180
degree centigrade.
190 something around that level, and atmospheric temperature is, so the difference atmospheric temperature will be around 30 degrees centigrade or so. So, the differential temperature will be around 200 degrees centigrade or so. So, under that situation, or in the previous case also, suppose we have a liquid water droplet and that is falling on a hot surface, again the temperature difference may be 200 or more than 200 degrees centigrade. Under that situation, we are reaching closely towards to a film boiling region. So, then what happens? We are reaching towards film boiling region. So, what happens when the liquid droplets falls on the hot surface? Okay. So, in case of droplet of liquid nitrogen and liquid air, the normal flow surface is the hot surface. So, when it falls on the hot surface, then the liquid starts boiling and then a film is formed, and that film, so film of the vapor is formed, and the film of the vapor, when it is becoming more sufficiently large, then what will happen? There will be some buoyancy force. Okay. So, it will get an upward thrust because of the film. So, the film gives a upward thrust for the bubble, for the droplet. Then what will happen? The droplet will come upward and then the vapor part will go, and then again droplet will fall down. So, droplet size is reduced, and falls back on the surface again. Droplet size is reduced and it falls back on the surface again, and again the similar blanket is formed, a similar vapor layer is formed, and then again upward thrust, like that. So, this phenomena continues till the droplet vanishes. Okay. So, this is what is called Leidenfrost phenomena. Okay. This one very interesting phenomena that is being observed in case of in case of droplets falling on hot surface, and it is linked with the boiling phenomena and particularly with film boiling phenomena. Okay. Now, next part is that we should have some idea on this hysteresis in boiling curve. That is already we have discussed. What happens is that in normal situation, that if this is the excess temperature, already we have seen this, and this is a log of Q dot S. So, it is heat flux at the surface. Q dot S is heat flux at the hot surface, and T is equal to excess temperature of the hot surface. Okay. And this hysteresis phenomena is first observed by Nukiyama in 1934. What is happening here, as we have discussed, that there is a boiling, that so this is the boiling curve. Okay. And so this is point A, then say this point, say we have seen B, then we have seen C, then there is a point D, okay, and then we have point E, says F, and here it is a point G. Okay. Now, what happens? It is supposed to go in this route, okay, but once it reaches here, it goes by this route, and then while coming back, it comes back in this route. Okay. So, this is happening the hysteresis. So, this is called the hysteresis phenomena. So, when we are going on heating, it should, for a controlled heating, it will go by the route, it should follow the route A, B, C, D, then E, F and G, but actually it follows A, B, C, D to G, and this is because of, as already I was telling, this uncontrolled heating, and therefore, this becomes very dangerous. So, our operation point should always be little lower than the point, somewhere in this region should be our operating point, because we should not go to this region. Similarly, while coming back, if we are any time by any chance at point G, and if we, for cooling purpose, for cooling, it should come back, it comes back through the path GFCBA, GFCBA in place of GFED, GFED, then CBA. So, this path is not followed while cooling. So, this is called the hysteresis operation, hysteresis in case of boiling phenomena. Okay. And latent frost phenomena occurs at point nearly equal to D. Okay. And at that point, at that situation, this latent frost phenomena takes place. Now, we will discuss about mechanism of nucleate boiling. As we told, the nucleate boiling can take place on the surfaces, and there will be a bubble to be formed. We can have different type of surfaces. One is called, say, 3 different type of surfaces, I will write, and this is, say, this is not wetting surface, this we can say the partially wetting surface, not wetted rather, and totally wetted surface. Okay. So, we can see that in this case the bubbles formation is like this, and for partially wetted surface, because the contact angle is, so this should be linear, this is the straight line. So, in this case the relatively this kind of things, and in this case it will be almost contact angle is no contact, it is almost that covered up, it is partially wetted by the liquid, and it is completely, I should say, I should draw like this, yeah, it is completely wetting, liquid is completely wetting the surface. Okay. So, this kind of situation that take place on the surfaces, and we know that this mechanism of nucleate boiling, when the formation of the bubble formation in case of these three, naturally we will be preferring, this is more preferred, because we know that liquid is covering almost all the surfaces. Here some amount of surface is covered by the vapor, and we know the heat transfer coefficient for the vapor is lower than the liquid. So, in this case more favored, because here in this case the heat transfer rate will be faster, because the liquid is directly contact with this rather than the vapor. Okay. Bubble formation is basically it's called nucleation, and that means the start of the bubble, and then, or rather I should say that nucleate boiling starts by two things, that is called, one is bubble formation, that is called nucleation, another is called bubble growth. Okay. Now, in case of bubble formation or in case of nucleation, just the bubbles are being formed, there can be nucleation in the liquid pool, this is called homogeneous nucleation, and another can be nucleation on surface, and this is called heterogeneous nucleation. So, under the heterogeneous nucleation, that it happens that bubbles grows on the surface, and it happens to the cavities or crevices in the surface. We can see that this is the figure where it says that how a bubble grows. So, this is the cavity on a surface. So, that will be surface roughness should be there, and in that there can be some kind of cavities and all. This is the cavity, and this is a growing bubble, and this bubble grows, and gradually this is the stage before it gets detached from the surface. Now, what happens is that we have to discuss that in case of nucleate boiling, that how a vapor or how a bubble gets stable, mechanically stable, and we will discuss what would be the various heat transfer correlations available to find out the values of heat transfer rate in a boiling situation, and particularly our interest would be towards the nucleate boiling situation. So, next class we will be discussing further details on that behavior of the bubbles and boiling phenomena. Thank you.